A grow light or plant light is an artificial light source, generally an electric light, designed to stimulate plant growth by emitting an electromagnetic spectrum appropriate for photosynthesis. Grow lights are used in applications where there is either no naturally occurring light, or where supplemental light is required. For example, in the winter months when the available hours of daylight may be insufficient for the desired plant growth, lights are used to extend the time the plants receive light. If plants do not receive enough light, they will grow long and spindly. Grow lights either attempt to provide a light spectrum similar to that of the sun, or to provide a spectrum that is more tailored to the needs of the plants being cultivated. Outdoor conditions are mimicked with varying color, temperatures and spectral outputs from the grow light, as well as varying the lumen output of the lamps. Depending on the type of plant being cultivated, the stage of cultivation, and the photoperiod required by the plants, specific ranges of spectrum, luminous efficacy and color temperature are desirable for use with specific plants and time periods. Russian botanist Andrei Fomentsyn was the first to use artificial light for plant growing and research. Typical usage: grow lights are used for horticulture, indoor gardening, plant propagation and food production, including indoor hydroponics and aquatic plants. Although most grow lights are used on an industrial level, they can also be used in households. According to the inverse square law, the intensity of light radiating from a point source that reaches a surface is inversely proportional to the square of the surface's distance from the source, which is a serious hurdle for indoor growers, and many techniques are employed to use light as efficiently as possible. Reflectors are thus often used in the lights to maximize light efficiency. Plants or lights are moved as close together as possible so that they receive equal lighting and that all light coming from the lights falls on the plants rather than on the surrounding area. A range of bulb types can be used as grow lights, such as incandescents, fluorescent lights, high-intensity discharge lamps, and light-emitting diodes. Today, the most widely used lights for professional use are HIDs and fluorescents, but recent advances in power efficiency and optimized light spectra show that high-powered LED systems can produce improved yields. Indoor flower and vegetable growers typically use high-pressure sodium and metal halide HID lights, but fluorescents and LEDs are replacing metal halides due to their efficiency and economy. Metal halide lights are regularly used for the first phase of growth, as they emit larger amounts of blue and ultraviolet radiation. With the introduction of ceramic metal halide lighting and full-spectrum metal halide lighting, they are increasingly being utilized as an exclusive source of light for both vegetative and reproductive growth stages. Blue-spectrum light may trigger a greater vegetative response in plants. High-pressure sodium lights are also used as a single source of light throughout the vegetative and reproductive stages. As well, they may be used as an amendment to full-spectrum lighting during the reproductive stage. Red-spectrum light may trigger a greater flowering response in plants. If high-pressure sodium lights are used for the vegetative phase, plants grow slightly more quickly, but will have longer internodes, and may be longer overall. In recent years, LED technology has been introduced in the grow light market. By designing an indoor grow light using diodes, the exact wavelengths necessary for photosynthesis are used to create LED grow lights that are used for both the first phase and the second phase of growth. NASA has tested LED grow lights for their high efficiency in growing food in space for extraterrestrial colonization. Findings showed that plants benefit from the use of red, green and blue parts of the visible light spectrum. Light spectra used: natural daylight has a high color temperature. Visible light color varies according to the weather and the angle of the sun, and specific quantities of light stimulate photosynthesis. Distance from the sun has little effect on seasonal changes in the quality and quantity of light and the resulting plant behavior during those seasons. The axis of the Earth is not perpendicular to the plane of its orbit around the sun. During half of the year the North Pole is tilted towards sun, so the northern hemisphere gets nearly direct sunlight and the southern hemisphere gets oblique sunlight that must travel through more atmosphere before it reaches the Earth's surface. In the other half of the year, this is reversed. The color spectrum of light that the sun emits does not change, only the quantity and quality of overall light reaching the Earth's surface. The color rendering index allows comparison of how closely the light matches the natural color of regular sunlight. Different stages of plant growth require different spectra. The initial vegetative stage requires a blue spectrum of light, whereas the later flowering stage is usually promoted with red or orange spectra. The ability of a plant to absorb light varies with species and environment, however, the general measurement for the light quality as it affects plants is the PAR value, or photosynthetically active radiation. This measures the useful light energy received by the plant, and the spectral measurements favor the blue and red portions of the light while ignoring in part the green and yellow portions, which plants generally do not benefit from. Light sources Metal halide Metal halide bulbs are manufactured in the blue spectrum light mimicking spring and summer bright blue skies. But they are now being made for digital ballasts in a pulse start version and can come in any desired spectrum from cool white to warm white and even ultraviolet heavy. Metal halide lamps are widely used in the horticultural industry. Ceramic metal halide Ceramic metal halide is a relatively new source of HID lighting. Horticultural CDM offerings from companies such as Philips have proven to be very effective sources of growth light for medium wattage applications. Combination MH and HPS Combination HPS-MH lights combine a metal halide and a high-pressure sodium in the same bulb, providing both red and blue spectrums in a single lamp. The combination of blue metal halide light and red high-pressure sodium light is an attempt to provide a very wide spectrum within a single lamp. This allows for a single bulb solution throughout the entire life cycle of the plant, from vegetative growth through flowering. There are potential trade-offs for the convenience of a single bulb in terms of yield. There are however some qualitative benefits that come for the wider light spectrum. High-pressure sodium High-pressure sodium lights yield red visible light as well as small portions of all other visible light. They are used as a supplement to natural daylight in greenhouse lighting and full-spectrum lighting, metal halide, or, as a standalone source of light for indoors grow chambers. The major drawback to growing under high-pressure sodium alone, is that plants tend to elongate from the lack of blue ultraviolet radiation. Modern horticultural HPS lamps have a much better adjusted spectrum for plant growth. The majority of HPS lamps, while providing good growth, offer poor CRI rendering which can make monitoring plant health indoors more difficult. CRI isn't an issue when HPS lamps are used as supplemental lighting in greenhouses which make use of natural daylight. High-pressure sodium lights have a long usable bulb life and 6 times more light output per watt of energy consumed than a standard incandescent grow light. Due to their high efficiency and the fact that plants grown in greenhouses get all the blue light they need naturally, these lights are the preferred supplemental greenhouse lights. But, in the higher latitudes, there are periods of the year where sunlight is scarce, and additional sources of light are indicated for proper growth. HPS lights may cause distinctive infrared and optical signatures, which can attract insects or other species of pests. These may in turn threaten the plants being grown. High-pressure sodium lights emit a lot of heat, which can cause leggia growth, although this can be controlled by using special air-cooled bulb reflectors or enclosures. LED LED grow lights are composed of light-emitting diodes, usually in a casing with a heat sink and built-in fans. LED grow lights do not usually require a separate ballast and can be plugged directly into a standard electrical socket. LED grow light models can be customized to emit only specific wavelengths of light. It is known that red, far red and blue light spectra have an effect on root formation, plant growth, and flowering, but there are not enough scientific studies or field-tested trials using LED grow lights to recommended specific color ratios for optimal plant growth under LED grow lights. The diodes used in initial LED grow light designs were usually 1/3 watt to 1 watt in power. However, higher wattage diodes such as 3 watt and 5 watt diodes are now commonly used in LED grow lights. LED grow lights are usually priced much higher, watt for watt, than other grow lights. Many manufacturers claim that LED grow lights have better photosynthetically active radiation levels than other grow lights. Fluorescent fluorescent lights are available in color temperatures ranging from 2700 kelvins to 10,000 K. The luminous efficacy ranges from 60 lumina per watt to 90 lumina per watt. Standard fluorescents are usually used for growing vegetables and herbs indoors or for starting seedlings to get a jump start on spring plantings. Fluorescents have an average usable lifespan of up to 20,000 hours. Cool white fluorescent lights are sometimes used as grow lights. High-output fluorescent lights produce twice as much light as standard fluorescent lights. A high-output fluorescent fixture has a very thin profile, making it useful in vertically limited areas. Compact fluorescent lights are smaller versions of fluorescent lights used for propagation, as well as for growing larger plants. Compact fluorescents work in specially designed reflectors that direct light to plants, much like HID lights. Compact fluorescent bulbs are also available in warm red, full spectrum or daylight and cool blue versions. Usable lifespan for compact fluorescent grow lights is about 10,000 hours. High-output fluorescent high-intensity discharge hybrids combine cool operation with the penetration of high-intensity discharge technology. The primary advantages to these fixtures is their blend of light colors and broad even coverage and reduced electric requirements. Incandescent bare incandescent lights generally have a red-yellowish tone in low color temperature. They are sometimes used to highlight indoor plant groupings but not as a true plant-growing light. Some incandescent bulbs specifically marketed as grow lights come with a blue filter coating which reduces the amount of red light the bulb gives off. Such grow lights have a brief life expectancy of about 750 hours and are energy inefficient, producing more heat than usable light. Light-emitting plasma Light-emitting plasma is a new light source that produces light very similar to PAR, which has been identified as the optimum spectrum of light in reference to healthy plant growth. Switchable, convertible, and two-way switchable, two-way and convertible lights burn either a metal halide bulb or an equivalent wattage high-pressure sodium bulb in the same fixture, but not at the same time. Growers use these fixtures for propagating and vegetatively growing plants under the metal halide, then switching to a high-pressure sodium bulb for the fruiting or flowering stage of plant growth. To change between the lights, only the bulb needs changing and a switch needs to be set to the appropriate setting. These are commonly known as conversion bulbs, and usually a metal halide conversion bulb will be used in an HPS ballast since the MH conversion bulbs are more common. Light requirements of plants. A plant's specific needs determine which lighting is most appropriate for optimum growth. Artificial light must mimic the natural light to which the plant is best adapted. If a plant does not get enough light, it will not grow, regardless of other conditions. For example, vegetables grow best in full sunlight, and to flourish indoors they need equally high light levels, whereas foliage plants grow in full shade and can grow normally with much lower light levels. In addition, many plants also require both dark and light periods, an effect known as photoperiodism, to trigger flowering. Therefore, lights may be turned on or off at set times. The optimum photo-dark period ratio depends on the species and variety of plant, as some prefer long days and short nights and others prefer the opposite or intermediate day lengths. Much emphasis is placed on photoperiod when discussing plant development. However, it is the number of hours of darkness that affects a plant unregistered trademark's response to day length. In general, a short day is one in which the photoperiod is no more than 12 hours. A long day is one in which the photoperiod is no less than 14 hours. Short-day plants are those that flower when the day length is less than a critical duration. Long-day plants are those that only flower when the photoperiod is greater than a critical duration. Day-neutral plants are those that flower regardless of photoperiod. Plants that flower in response to photoperiod may have a facultative or obligate response. A facultative response means that a plant will eventually flower regardless of photoperiod, but will flower faster if grown under a particular photoperiod. An obligate response means that the plant will only flower if grown under a certain photoperiod. lux and lumen are photometric units, in the different wavelengths of light are weighted by the eye's response to them. This makes them an appropriate measure of the lighting level in a horticultural lighting system. Instead, lighting levels are quantified as amount of radiation in the wavelength range from 400 to 700 nanometers, or photosynthetically active radiation. It can be expressed in units of energy flux or photon flux. According to one manufacturer of grow lights, plants require light levels between 100 and 800 I1/4 mol Ma 2 ZAR1. For daylight spectrum lamps, this would be equivalent to 5800 to 46,000 lumina per meter 2. See also, chlorophyll, photosynthesis. References. External links.